Hello, I'm Michael Parabashi, and today I'm going to be looking at the implementations of lithium-ion battery cell liquid cooling for electric automotive applications. This is based on the research paper named below, and we're going to talk about that more later. To start out with, we're going to need to know some background information about lithium-ion cells. On the right, there is an image of a lithium-ion cell. And we're going to be looking at the flat pack style rather than the 18650 style. In the flat pack style, we can see that it's a very thin and wide battery pack, and it has this sort of a structure inside, where there's multiple layers with the reactive materials that store the energy inside the cell. And then these join together to form the tabs that come out of the battery pack right here. And some of the importance of this sort of a design is that there can be temperature gradients within the cell when this battery heats up. And that's part of what we're going to be testing today. So, general idea of how these batteries work is they take chemical energy and turn it into electrical energy. And as a part of that, they lose energy as heat, particularly with heavy loading. As the load on the battery increases, those losses are going to also increase. Two sources of those losses are ohmic losses, so this is from the internal resistance of the cell. And next, chemical losses, as the chemical reactions that produce the electricity are not perfectly efficient, and some of the energy is lost as heat. Next is that batteries do have a maximum temperature that they can withstand. Above that temperatures, and the reactants inside of the battery will decompose along with some of the membranes and other stuff that's in the inside of these batteries. Next is that lithium-ion battery packs, such as the one you see on the top right, are often stacked to form large packs to meet the electrical requirements, so higher voltage or the ability to dump higher amounts of current. And these battery packs are very close physically. And we're going to see an example of that right here. This is a battery pack from an electric vehicle. We can see that this single battery pack is made of several smaller battery packs, and each of these are made from each of the battery cells. Each one of the cells is these skinny lines that goes in this direction. And you can see they're all stacked right next to each other. This makes cooling a significant concern for these cells, as the heat needs to escape from the cells to the outside world to prevent overheating of each one of these. So today we're going to look at cooling systems that will help to address this issue. And this will not work for not only automobiles, but even bulk storage for power grid systems and other applications. But the specific cells and the specific applications we're looking into today are the automotive industry. To first understand what some of the thermal management importance of the thermal management is that there will be an inconsistent current density if the temperatures are not managed. What this means is that different cells will produce different amounts of current at a given discharge rate depending on how hot they are. And then this will then lead to inconsistent states of charge, which means some cells will be a higher voltage than other cells and will make the whole battery pack unable to function as a whole. In addition, high temperatures will have a decomposition of the battery reactants and the layers and films in between the reactants. And with this, we're going to have a reduction of the cycle life of the battery. So the batteries won't be able to take as many charge cycles. Not to mention, this can cause a fire hazard. An example of that we can see from the Washington Post. They had an article on a Tesla that had recently gone up in flames. And this was a battery issue. It was diagnosed as a battery issue. And part of the research Tesla did on the battery pack, they found what the cause was. That was not released, although their fix to it was they increased the charge time, meaning that batteries will take longer to charge and they'll have a lower load when they are charging. In addition to that, they also reduced the amount of power that they can pull from the battery at any one time. Both of those can be linked to temperature. So it may have been a temperature problem, a thermal management problem inside of the battery pack that caused this fire. It may not have been. Those are symptoms that could have caused the problem, although it was not officially reported what the definitive cause of the problem was. So let's look at a simulation of a battery pack that under load. Each one of these vertical lines represents one of the battery packs, and they will each heat up on their own. There's a small separation between these, which may or may not be present in a finalized battery pack. And we can see that the center one has the highest temperature in red. And this is, of course, because what we talked about. It's very challenging for the heat that's in the center pack to escape to the outside world. In any direction, it's challenging for it to escape. And so this is greatly going to impact the performance of this center cell. So we're going to take a look at some cooling systems that will hopefully address this issue for a pack and individual cell. So we're going to look at several different configurations. The first configuration is the Facecell Cooling. And in this configuration, the pouch cell is directly touching the thermal interface material on its large surface area, so one of the large faces. And then that thermal interface material is then wicking the heat to the cooler on the back. And this cooler is a liquid cooler where coolant is flowed through these pipes through the cooler to remove the heat from the cell. My hypothesis for this system is that this will have exceptional cooling performance. There's a large area touching the cooling system, and so it will have a very good ability to remove heat. Unfortunately, I predict it will have a poor energy density. There is a lot more additional hardware needed to run this single cell than there would be if there was no cooling system. The next configuration we're going to look at is the single side cooling system, where the pouch is lined up vertically along with this cooling system, and the thermal interface material is then, of course, connected to the cooling system. Here, I expect pretty poor cooling performance because the surface area that's touching the thermal interface material is very, very small, and so there's going to be very little heat that can be wicked out that way. In addition to that, I would expect it to have exceptional energy density because it's very easy to see how many cells could be stacked on top of this left and right. So this has the benefit of being very scalable, but at the cost of probably having low cooling performance. Next, we have two configurations are encapsulated in this image. The first configuration we can see right here in this image is called the hybrid cooling system. We have a graphite sheet that is designed to pull heat away from the center of the cell out to the cold plates on both sides. The next configuration is the dual-sided cooling configuration, where there is no graphite sheet and the heat has to flow through the cell to reach the edges where it can be taken away by the cold plate. I expect both of these systems to have moderate cooling capabilities. There's a larger surface area on these contacting the cold plate, so they should have a moderate cooling capability. And I also expect a very good energy density because it's easy to see how we could stack many, many, many cells on top of this and form a large battery pack while still only having two cold plates. So the way this cooling system is going to work is we are going to have a chiller which supplies cool liquid to the heat exchanger, which then exchange that with the coolant fluid. This is pumped by the pump, as you can see here, which then goes to a mass flow meter to determine what the flow rate is, how much liquid is moving to the cooling system. Next, we're going to measure the temperature before the cell. It goes through the cold plate, where it's removing heat from the cell. Then we're going to measure it after the cell. It's then going to repeat this cycle over and over and over again. This whole time, there's going to be data acquisition on all of the different temperature sensors on the cell pack, and we're going to talk about that next. There is going to be several different discharge profiles to get an understanding of how the batteries behave under different loading scenarios. First is 3C, which means it's going to be 3 times the capacity of the cell, which is a discharge current of 27 amps. This is quite large for a single cell. Then all of the different test profiles are going to begin at fully charged, which is 4.2 volts, And the end voltage is then going to be 2.5 volts. We're also going to run the same test with 4C discharge profile, and that is 36 amps. Lastly, 5C, which is 45 amps. We can see the loading is substantially increasing as we go down the tests. Next, the temperature monitoring system. Here, there's going to be many thermal couples across the cell. In fact, there's 14 of them. And each of these data will be logged for the entire duration of the test. This will then all be plotted, and we can see the plot here on the right. To understand this plot, first we have the graph of the current, and that is this black dotted line. Here we can see how the current is just a step function. We're going from drawing it, and then we're going to stop drawing current, and that's it. We can also see the voltage. It slowly decreases. That is the gray dotted line. Next, we have all of the temperature sensors, which all form a peak and then fall off. And they fall off right after the cell no longer experiences load. We can see here, zoomed in, the peak of the graph, and we can see what each of the maximum voltages are for this graph. So, running the tests, we can see several different we can see that there's a similar shape and structure of all of the plots, but there is differences in many of the temperatures. So for instance, as we expected, the face cooling method had performed the best. There is the lowest temperature of 30.4 degrees compared to all of the other ones, and the gradient is fairly small, with a gradient of only about 1.5 volts. We can see next the hybrid cooling system performed fairly admirably at 37 degrees or just a little bit under compared to all the others. Next we had the double-sided cooling system. Here it got all the way up to 41 degrees. And lastly, in worst, which was single-sided cooling, almost reached 46 degrees. And not to mention that, it also had a very large thermal gradient across the cell. We can see that these temperature profiles are matching what we're predicting. But let's see if that continues as we increase the discharge rate. Next, we have the 4C discharge rate. Here we can see that the battery temperature, the maximum for this face cooling, is 32.6 degrees. It's very high. It's high, but not very high. It's reasonable, and this cooling system is still outperforming all of the others. Next, we have the hybrid cooling system, which is almost 10 degrees hotter than that of the face cooling. Next, we have the double-sided, as we expected. And lastly, we have the single-sided cooling, reaching almost 52 degrees, with, again, a very large spread across the cell. Continuing on to the 5C discharge, we can see all of these trends seem to be amplified. Again, the face cooling method was the best at only 35 degrees, or just a little bit above 35 degrees Celsius. And then next we had at 52 degrees Celsius, the double-sided. We had next the hybrid cooling at just above 46 degrees. Then we had the double-sided at 52. And in last place, we had the single-sided cooling at 58 degrees. And we can see here that the trend has continued. So let's look at that. We can see consistently that the face cooling outperformed everything else, and by a fairly large margin. Compared to the hybrid cooling, which was in second, the double-sided cooling in third, and in last place we have the single-sided cooling. In addition to that, that same trend applied to the temperature gradients, where we can again see that the face cooling has the best temperature gradient, and the single-sided cooling has the worst temperature gradient. So what we can take away from this is that the different cooling systems, the differences were amplified by the larger discharge rates. In addition, we can see that the temperature is substantially affected by the cooling system. Different cooling systems perform substantially differently. Lastly, we can also see that the temperature gradient follows the same trend and is also substantially affected by these cooling systems. So let's take a look at some of the direct results and direct takeaways from this system. We can see that each discharge profile exhibited the same shape. They all had the same peaks and they went to the same troughs. But the different discharge rates had differences. The higher the discharge rate, the larger the temperature gradients, and the larger the temperatures. Next, we determined that face cooling had the best overall performance, with the lowest temperatures and the smallest temperature gradients. We also determined that the single-sided cooling was the worst. It had the largest temperatures and the largest temperature gradients. This being said, the hybrid cooling method was substantially improved on both the single-sided and double-sided cooling system, which means we might be able to, depending on the materials and the application, this might be the most effective cooling system, particularly for larger battery packs, because it's very scalable. So the hybrid cooling system in some applications may be the best option. So let's take a look at what the importance of this entire research, what it says, how does this help? The first thing it does is it quantifies these different cooling systems. This way, someone like myself, an engineer, I can use these numbers and I can run models and do simulations of these battery packs with the information that's been collected here. I can determine that one particular system might outperform another particular system in the application I'm looking for. Not to mention, there are places where you're concerned about power density rather than necessarily anything else. So the battery might not run for very long, so it may never reach a steady state temperature. And so maybe no cooling is required, or maybe some cooling, and that could just be the single-sided method. And so numbers that were presented in this research paper, along with all of the other testing that was done, can help determine what the best cooling system is for the application at hand. In addition to that, some of the physical properties of the cells result in differential cooling. For instance, one of the things that was found in the paper was that the different battery tab materials, one of them was made from aluminum and one of them was made from copper, and they had different temperatures at the tabs. And that is attributed to the fact that the thermal conductivity of the aluminum tab is substantially lower than that of the copper one. And because of that, that might affect how the cooling system is applied to the battery pack. You might want the cooling system on the side that has the copper tab. That might help cooling performance. Or you might want it on the one that's aluminum to keep that side below the temperature threshold. These are things that can be analyzed now with the information that has been presented. So, all this information came from two different research papers, but the majority of the information came from the research paper comparison of different liquid cooling configurations for effective thermal management of lithium-ion pouch cells for automotive applications. This was where all of the data and everything came from. I took a single graph or a single diagram, and this was of the individual cells and the thermal gradients to help explain the idea of having gradients inside of cells. That came from the performance weight trade for thermal management systems of lithium-ion batteries. And I thank you all for watching. I hope you enjoyed. I learned a lot making this. I learned a lot about different cooling systems and how cooling systems will affect the battery performance. And I hope you all have also learned something about this.